Well, good morning, gentlemen. So I hope that we'll be joined by a few more. I thought there might be a little quieter this morning. So, welcome to NDC London, day 2, and a talk on C++ and the type system. So, why? Why this talk? I usually like to start by thinking, well, why would I talk about this subject? Why would anybody listen to this? Why did I come up with this one? Well, I've seen a lot of people using C++ and some C for some time, and they use primitive types for a lot of things. There is a lot of help in the language that you can use, and you can write essentially your own language inside C++, rather than using what you're given. So here are 3 things that I think are important, and I would like them in this order. I want our code to help me to avoid avoidable mistakes. Stop me doing things that I don't want to do, things that I shouldn't do. And I want that at compile time, if I can get it. I don't want to have runtime crashes. I want to get the compiler to say, no, you can't do that. So how do we do that one? That's one of the things we're going to look at. The other important thing, or amongst the important things, is runtime cost. Okay, so if I have this and I use lots and lots of features in the language to help me build up my stuff to prevent this, I don't want to do this basically at 0 cost. Because if I do this at extra cost, oh, you can do this in this safety stuff, but it's slower or bigger, or generally gets in the way, then people are not going to do it. They're going to go back to the old way. They go, oh, I'm just going to use an int here, or whatever. So people go back to unsafe coding styles because it's slower. So I want to show that actually we can have our cake and eat it here. So we can say we can have our safety, and it has 0 cost at runtime in terms of memory and speed. It would also be nice if I could put this into a library and say, let's reuse this. So I don't have to do this again and again. How do I make it reusable, generic, flexible, those words that developers love? So we don't have to re-implement every time. So that's basically what we're going to look at today. So a little bit of history about programming and types. When machines first came out, you programmed the machine code or assembler. And essentially, it's typeless. There really isn't much in the way of types going on in there. You have some basic kind of things inside the machine, if you're lucky. Integer, the machine word, is the basic thing of this one, and you can use it as an address. So you can take an integer, turn it into a pointer to an integer. Assembler just says, yeah, it's a register, I don't care. You may have some things where there's slight differences. You may have some some floating point things on more recent machines in hardware than in old stuff. You get machine efficiency, that's great, but it's at the cost of programmer effort. You've got to do a lot of work to do this one. You basically have to go, okay, here's what I want to do, and then you have to translate this into the world of assembler and pointers and addresses, and you make sure you get it right. There is domain knowledge in there somehow, but it's inside the program. You can't see it obviously. And if you've ever done an assembler, you'll see here's the assembler, and here is the per line comment that actually tells you what's going on. It's not easy to decipher or work out what's going on. It's easy to make mistakes. There's a high maintenance cost of programming an assembler, which is why most people don't do it these days. Okay, so what comes after that? Well, after that, there were typeless languages like B and BCPL, which were a step up from assembler. It did all of the allocation for you, registers and other bits and pieces like this, but basically there was almost no type safety. So an example from BCPL, 3 times brackets 4 plus 5 would give you the value 27. If you miss out the multiplication by mistake, actually what you end up calling is a function at address 3 with the value 9. This is obviously a path to madness, and trying to debug this or work out what's going wrong is kind of fun. Okay, the C preprocessor, for instance, by the way, is simply like this. Great line from Kevin Henney yesterday. This is it's instead of strong type safety, it's string type safety. So everything is basically stringly typed languages. So that was sort of kind of where we started. And then the next thing is we started adding more types into this one. This is where you get C and people using C++ based around the primitive types. It stops you making those mistakes in terms of integers and pointers. It says, oh, you've got to do a cast for that. Okay, yeah, it's fine. So it stops those mistakes. You get the high machine efficiency, which is where C comes from, and C++ inherited that one. Better programmer efficiency. So you have integer pointer and float pointer and char pointer and other things like this. So you get some idea of what's going on in there. You haven't got any extra stuff. You haven't built any extra layers. You're still using what's underneath, though, integers and floats and type pointers. To this, they added structures and aggregates. So you've got structs and arrays and other bits and pieces. So this maps fairly well onto your assembler. So you get that efficiency. Not much abstraction, though. So C gives you abstraction through files. You can do modules primarily. But you have to translate. Still, there's a translation there because you go, well, this is how I'm thinking. I can't do this sort of kind of one-to-one that I might do well with objects. And there is little opportunity for compile time checking, so you might end up with a lot of static analysis tools to try and work out what's going on, particularly in safety critical things. This is where I'd like us to have a look at today, which is this higher level C++. How can we use the type system and using a lot of types to create lightweight abstractions that are going to increase the amount of domain knowledge we can put into our program without sacrificing that efficiency? So how do we get more stuff in there but still retain the machine efficiency we had from the previous ones? And the interesting thing about a type system is that it's a proof system. It says 100% you can either do this or you can't. You can add these two together or you can't. And it's done at compile time, and there's no ifs or buts about this one. It's legal or it's not. And I'm trying to see how we can make it so we can use that to avoid problems. How do we use the type system to basically say, you can do this, you can't do that, and stop problems happening at runtime by converting into compile time errors? If you do this well, you get code safety, you get more reuse. Bjarne Strustrup likes this, and he's trying to avoid people using primitives in interfaces. Okay. Compilation is remarkable. It's a wonderful thing. So here we have a picture. On the left-hand side, we have our runtime. And you'll notice at runtime, assembler, or C, C++, they all basically using machine types underneath. It all compiles down to the same thing. But you'll notice at compile time, in assembler, we basically have nothing. Because once you've assembled it, that's it. In C, you have some of the language types, so you basically get the ints and floats and pointers, etc. That information is thrown away. So everything in the orange is just thrown away. For the C++ one I'm talking about, we're going to add our own application types. So we're adding lots and lots of stuff into this type system, and we're then going to throw it away. And at runtime, we're left with exactly the same thing. And so we're focusing on that top right there about application types. Okay, some little small white lies here. C does have things apart from the language types, has some small application types such as structs, and C++ has some runtime type information, which is obviously at runtime, not at compile time. But the big picture of this one is we can use lots of types and then throw it away, and we don't have this at runtime. Okay, let's have an example. Let's get down to some code. End of big picture for the moment. Date, int, takes 3 integers. What are the parameters? How do you know? Well, you've got to go and look at the documentation. Or you have to go date, int, year, date, month, int, day. And there's nothing to stop you getting this wrong. There's nothing to stop you putting them in the wrong order. When will this show up? It'll show up at runtime, not at compile time. It would be much nicer to say date, take year, month, day, and it's very clear what those parameters are. which order you should put them in. If you try to put them in the wrong order, it won't compile if they're separate types. Okay, we're in a much better place already. It's unambiguous, it's expressive, we know what this is about. If we try to do this just by having an alias, a type def, so I'm using the C++11 alias features here. If I just said using year equals int, that doesn't actually do anything because it's a type alias, and therefore, if I said using year equals int, using month equals int, they are actually the same type because it doesn't introduce a new type, it's just an alias. So we can't use that. We have actually to create our own classes like class day, class month, etc. And this would catch them at compile time. Let's have a look at another example. What happens if you're trying to do things with physical units? So meters and seconds and some measures of length and time, and there's all of the 7 SI units to deal with. Meters plus seconds does not make physical sense. And the compiler goes, you can do that if you want. If you do them as floats, you could do that. If you do them as just meters and seconds. I want the compiler to tell me I shouldn't be adding length and time together because it just doesn't make sense. Notice on the second part there, I've got feet and meters. They're both lengths, but I can't just add feet to meters without some conversion. It doesn't work. It gives me a nonsense result. If you're lucky, it gives you a result that's obviously wrong. If you're unlucky, it gives you a result that's believable. So at the top right of this, you'll see these wonderful little pictures which are from the Mars Climate Orbiter. And the Mars Climate Orbiter, this is hundreds of millions of dollars worth of kit. Lockheed Martin and NASA managed to screw this one up, unfortunately. And the problem there was that the interface had pound seconds, so imperial English units, and one of the other parts was using SI units with Newton seconds, which are out by a factor of 4.45. So instead of that lovely little curve coming on the top and going round Mars, it came in 4.45 times too low, bang, straight into Mars. If those guys who are spending hundreds of millions of dollars on this can get this one wrong, what chance do we have? How likely are we to make these errors? I'm going to show you techniques that will stop these errors 100% if you use them. So it's still, you can write nonsense and it will still compile. So one of the basic things here is a thing called whole value pattern. This was invented or named by Kent Beck, the extreme programming guy, first in Smalltalk. And this is, right, okay, we're going to create class year like this, which is just holds this year. That's all it's doing. It's nothing, there's nothing special about this one, but it's a different type. So the second part on this one, the operator double quotes, C++11, so-called user-defined literal. This now allows me to write typed constants. So instead of just saying year y equals 2016, I can now say 216 underscore year, and that will return something of the right type. The other thing to notice is the explicit constructor. You can't automatically convert from an int into a year type. You actually have to say, I want the year parentheses, whatever. So this means that you can't accidentally pass these things around. You can't create one by mistake. Again, safety here. Coming out of this one, though, so that's explicit going in, stops that conversion, because that's an unsafe conversion. We want to control that one. Operator int is a user-defined conversion, an implicit conversion out of the class. So you can say, right, okay, how do I get that value back out? If we do this, we can actually just convert everything back into integers, do the arithmetic, and we're okay to go with that. We can actually still do stuff. This is giving us a start. It's not the end yet. So it's a widening conversion out, and that's safe. Not foolproof, and it gets boring when you have multiple types, because you can imagine that month is going to look the same, day is going to look the same. We're going to use this a lot, this pattern. Of course, when you see repeated code structure, templates are your friend. Templates are code generators built into the language, and they help you with repeated structure. So in this case, what I've done is taken class year. We can now call it class unit. That's the name that Bjarne Strustrup has been using, so I've been using that one, and now I'm going to template it. I'm going to template it on essentially just a number to make them different types. There's nothing special about the unit type there, it's just a list of numbers, and it means they're different. Same thing, but now I can say year is a unit of year type, and month of month type, and now they're 3 different types. So I can take this, I got my library class, and I can make them different. Now I've got a type-safe API, I don't need to repeat myself all the time. This is as efficient as using integers. All the functions in line, there's no runtime overhead here. Yeah? Absolutely, you can. So if you wanted, you could put that in a header file. For instance, if this was a date thing, you could put using in your header file and see this one. So if you had a date.h or whatever, then you would put in, you'd have this unit, you'd have year, month, day, and then your date one, all of that lot in one header file that other people can see. Absolutely. That's a start. We've wrapped up an integer, but we know that it's a constrained set of values. We don't want to be able to create things out of a certain range. So here is a technique we can use with constructors. So const expr is something that comes in C++ 11 and was made much more useful in C++ 14. So this means this can be done at compile time. So it's on a constructor or a function, it says it can be run at compile time. Whether it is or not depends on how it's used, and so there's a context in which it's used. So you can see at the bottom 2 lines, the first one is a runtime check, and the second one is actually a compile time check. So this one here, you can say, right, okay, my unit one like this. Notice on the unit type I've got 2 extra parameters, which is the low and the high values. So I can now say, aha, look, check at compile time, or when you try to create this one, that it is valid. If you're doing it at runtime, it'll do a throw. Okay, you can't create one of these, that's fine. If you do the throw at the compile time with const expr, you'll get a compiler error. Now, it may not give you a particularly nice compiler error, but it will actually give you a compiler error. So you can now, at the bottom, that bottom line will not compile. So I can say that's out of range. So now I can say, look, it's of type, it's like this, and it has this range, and get that checked. So we can do runtime and compile time checking. The compile time check has no runtime overhead. The runtime check obviously does. So up to now, we have just been looking at labeling our types. We haven't done anything particularly special with them, and we have not done anything with operations. We've said, okay, we're going to wrap this one up. When we want to do something, we'll take it out of this class, use the domain conversion implicitly, do our arithmetic, and then we have to decide whether to put it back in or whatever we can do, what we choose to do with it or print it out. This is error prone. We've got rid of some of our errors. We got rid of passing the wrong thing to date, but we haven't got anything about what we can do with years. Some operations are valid and make sense, physical sense, and some aren't. So we now need to start looking at the other side of this one, which is operations, and moving on from just labeled types. So we're going to make the conversion out of our thing explicit. So this is the same as before, but you'll see now in this explicit operator int. So conversion out. And I'm going to drop all the const exprs after this one, because otherwise the slides just get too big. Okay. Now you say, I can't create a year unless I explicitly type year. I can't actually convert it out into an integer unless I say I want an integer. So we've now got conversion control in and out. My operator plus, I've just said, look, it makes sense to say year plus an integer, or integer plus a year. So I can say 2016 plus 1. So year 2016 plus 1 gives 2017. But it doesn't make sense to say year 2017 plus year 3. What does add 2 years together? It doesn't make a difference. It doesn't make sense. So we can decide what operations make sense in our domain and which ones don't. So we can choose. We can now be explicit about what is allowed and what's not allowed. So date plus int, you go, yes, okay, that makes sense. So for dates, we can add in extra things. We can say what we decide what date plus int would mean. Maybe that's going to add a number of days. Date plus 1 will be tomorrow. Int plus date. Date minus date, that makes sense because of how many days in between would it be. Date less than date. Yes, that's obvious. There's some ordering between those, and we can do equalities. So some things will give us date, some will give us int, some will give us bool. Date times int. What does it mean to say 2 times today? Makes no sense. So we have to decide which operations make sense, which ones don't. But for instance, with money, you can say, well, money times a floating point. Yes, that's fine. That's an interest calculation. That's a very common thing to do. But money plus a float doesn't make sense. Certain operations do, certain operations don't. And there's a whole pile of sort of kind of mathematics around this, one with groups and rings and all those other things like that, if you want to get into this. How do we get the point where we can have the desirable ones? How can we say what we want and what we don't want here, but without having to spell it out every time? How could we make that more reusable, more generic? How do we avoid all the boilerplate and repetitive code? Okay, let's have a look. So, first approach is that we can let the client do it. And there happens to be something in the standard library that will do this. So if you have operator equals equals, which is a fairly straightforward thing to do, and operator less than, you can now include relops. This is something that was in the 98 standard, and it defines the other operations, like less than or equals, in terms of less than and equals equals. And what it has inside is some templates, some basic templates, like operator greater than is just operator less than, but with the arguments turned around. So this is, you can say, well, I publish these ones, and I'll let the client decide what he wants that. The reason it's done this way, and in a separate namespace, is because they're very big, powerful templates. Operator greater than, matching 2 T's, would just match everything. So that would give you operator less than on things that just don't make sense at all, which is why it's constrained. You can't use this to define your own class, though. It's a bit of a quick, cheat way around it. But it's there. So that's one option. We're not going to take that one. We're going to see a little bit more, and that's only defined for the relational operators. So here's a technique thing called CRTP, the Curiously Recursive Template Pattern, or Curiously Recurring Template Pattern. This was used over 20 years ago. There's a book called Scientific and Engineering C++ by Barton and Nachman, who do a lot of this. This is essentially doing the same as a virtual function, but it's doing it at compile time. And it's a rather fun trick. When you first see it, you go, really? What's going on here? So class year inherits from ordered of year. You appear to be inheriting from yourself, or a template parameterized on yourself. Well, the reason for this one is that why we do it this way, this is, as I said, a compile time version of virtual functions. If you just do it without virtual functions, you could, with virtual functions at runtime, class year inherits from ordered, and then ordered, which is the base class up here, would have virtual functions that would say, right, I want to use the operator less than that's in the derived class. And so it would say virtual operator greater than, called the derived class is less than. So it would use virtual to do the downcast. But that's done at runtime. What you need to do is to get that same downcast done at compile time, which is why you need to have this technique here with a downcast, a static cast to derived. In order to know where to do the downcast, you have to pass in the derived class, which is why it's year public ordered of year, so that you can pass into the base class the thing it's trying to downcast to. That's the way it's done. It's a very powerful technique. When you get your head around it, you go, oh, I can do lots of things here. So if you're used to thinking in terms of object-oriented stuff and virtuals done at runtime, you can do the same things now at compile time. And so here at the bottom, I can see that I've got an operator greater than defined in terms of operator less than. So that derived downcast is done at compile time. There is no overhead to that one because the class has no size, so there isn't any pointer adjustment or anything at all. It's just a cast. It's all compile time stuff, and this is sometimes referred to as compile time polymorphism. So as I said, it's like virtuals, but done at compile time. Why do it this way rather than with a virtual? Okay, so imagine I had this as an unsigned char. If I added virtual to that, any virtual methods, then it would add in a virtual table pointer. So vtable pointer, so on a 64-bit machine, my 1 byte unsigned char has now got an 8-byte pointer followed by 1 byte. So it's now gone from 1 byte to 16 bytes. 16 times larger. Or if it was an int, it would be 4 times larger. I'd have to do a virtual call. So I'd have to do this call resolution at runtime. So that's slower. So it then takes, instead of being resolved and inlined, which basically has 0 overhead, it's now going to take 15, maybe 20 cycles to do that, to do a virtual call at runtime in direction through a pointer. You can't do const expert, you can't do compile time stuff anymore, because it's a runtime thing if you use virtual rather than using these techniques. So you've pushed things to runtime, you made things slower. It's unlikely you can inline it, or it depends how it's done, but if it was pure virtual, you wouldn't be, if it was just virtual functions, you probably wouldn't be able to inline it. Inlining is a huge performance benefit. And also, the branch prediction in your CPU is going to go, I have no idea, it's a virtual function. Don't know. It's going to have to measure it at runtime. Whereas if you do this one, it's all inlined, you've got no overhead here, and there's no branch prediction because it's all inlined. It's a very common technique used in libraries like Boost. You'll find some libraries use it all the time. Very useful technique to get your head around. So let's now look at physical quantities. So this is back down to the Mars climate orbit problem. So I've got quantity at the top there, so it looks fairly similar. But notice I've added some extra things into this one here. So instead of just, I've added type name v, so that says I can parameterize the type. Am I storing a float or a double or an int or whatever? I've got a second one, unit sys. And this is then for saying, okay, this is a templated parameter that tells me what type of system I'm going to be using. So specifically here, am I going to be using SI units, or am I going to be using the English or Imperial units? And then I've put 3 additional template parameters there. I could go all the way up to 7. So these are the indices, the exponents for the dimensions. So M, L, and T for mass, length, and time. I can now define operators, operator plus and operator divide on all the other ones. So operator plus just says you can only add quantities of the same type. I can only add things which are the same with the same units, and they happen to be the same physical unit representing. So I can't add mass to length. So the M, L, and T in this case are indices for this one. So as an example, see the bottom here, meters. I'm defining, say, that's a float, and I'm going to be using SI units 0, 1, 0, so mass 0, length 1, time 1, so that's times 0. That says I'm dealing with a length quantity, so I'm doing dimensional analysis. Seconds, mass 0, length 0, time 1. Now if I do meters plus seconds, like on the bottom, it's going to say you can't do that. You can't add meters to seconds. It doesn't make physical sense. There is no operator plus for these, because you can only add things which are the same types. Operator divide, however, is a little bit more fun, because notice that says, well, okay, I can only do things of the same type and the same unit system, so immediately I'm in a good place there. But mass 1, length 1, time 1, mass 2, length 2, time 2, and then I say, okay, I'm now going to do some arithmetic. So I'm going to say the output has the same type, same units, but mass 1 minus mass 2. So I can now start to do arithmetic on the exponents. So when I do meters divided by seconds, instead of what the answer will be float SI units 0, 1, minus 1. In other words, meters divided by seconds gives me a velocity. So it says, here are the calculations you can do. And by the way, I'm going to keep track of all those types. Again, 0 runtime overhead here. Why? Because this is all in the type system. We throw it all away. We've got a proof system at compile time that says you've not done anything silly, or here are the class of silly things that I've stopped you doing. And you can always write silly stuff, of course, but it's thrown away. So we're getting these conversions. In our case here, the conversions we're doing are the exponents It stops physically impossible calculations and stops the mixing of units, the SI units and imperial units. We can do related flavors here. So multiple currencies you could do similarly like this. You could say, okay, I can have a currency in this value, currency labeled with this value. I would then have to define what conversion would meant between them. So if I wanted to convert pounds to dollars or euros, I could stop myself adding pounds and euros together. Because all of this is all of that information that we have, that rich type information, is thrown away at runtime, we can't do in C++ what you can do in other languages, which is do runtime reflection and find out what types things are, or do calculations at runtime. You can do calculations at compile time, however. So in C++, one of the techniques that's often used, a little bit of template metaprogramming, is publishing your template parameters out to the outside world. So you republish what comes in. So I've got V, U, M, L, and T, and I'm republishing them. So you'll see value type. So for instance, if you have a vector of T, you'll find inside there is a type def that says value type that tells you that the vector of T has a type of T that allows you to be able to take a container and find out what's inside it. Same thing here. I'm republishing the exponents and unit systems, etc. So that's all just static information that's in the type system, but there's no overhead to it at runtime at all. So why would you want that? Well, okay, in the middle here, length and time. So I can say, oh, I got a float of SI units. I then want to have a time unit that's compatible. I say, well, it has a quantity of length type. Yes, I want that to be type. I want this to have the same type as that guy. So if I change it from float to double, that would also ripple through. I want to have it the same unit system. So I can do some simple calculations through this compile time reflection. I may say I can use the templated alias like this. I say mass is always going to be 100 for these ones here. But I can then also decide whether I want to have floats and doubles or some other types in there. I can do things like this. If the unit system equals SI units, then print out this one here. Because that if is done at compile time, then that will be dead code. If it wasn't there, the compiler would eliminate it. In C++ 17, you could even do if const expr. So that is how do we tailor these operations? So the next aspect of this one here is we want to be able to use some way of saying, well, I want plus for this guy, but I want not for this. So for instance, when we looked at date and money, date we said we want to be able to add date and integer. We didn't want to be able to add money and integer. We wanted to do date money plus money, yes, but not date plus date. So I've got a short little thing here, operator traits, that's basically a table that says, here are the operations that I want, and here's the ones I don't want. So I can put, I don't want these ones here, so my base one here of add scale or add value, and now I can do these operator plus. There's two versions here, so the first one is adding an integer to something, and I've put in an enable if. Enable if is a way of limiting the overload set for a template, and basically says, if operator traits add scalar is true, then this is enabled. If it's not, this template does not exist. So it uses this technique called SFIN-A. Substitution failure is not an error, and it says, if that's not true, it's not there, but don't complain. Don't throw an error if this template is not there. If you try to use it, it will, but it doesn't say enable if won't throw that kind of, won't complain. It just takes that template away. So I can say, I can do t plus integer, or I can do t plus t if add value is true. So that will be the library code. And then how do I use that? Well, the client code says, okay, here, operator traits for year, I'm just going to say add scalar. I want add scalar, I don't want the other ones. So I can say, here are the operations I want. I can enumerate those ones. That will use the enable if, turn on the templates for the relevant operations, and now I can say year plus 2, it goes fine. Year plus year is a compiler error. So that's kind of fun. That allows us, notice here, the use of these things, once you've done all the rest of them, is simple. So I'm trying to get it so that there is zero runtime overhead, but also zero sort of developer overhead to using these types once you define them. The code looks just as you would have done if it was integers. So where are we? We've done a load of stuff here, thrown a pile of things in. Let's have a look. So on the left here, I have my main. So I've decided I've got distance here, which is this. So I've got all this business with const exprs and user-defined literals, 5.2 meters. I have all this physical dimensions, all that ML and T type of extra stuff. I've got this unit types about what we can do. I'm using CRTP for the operator inheritance. So this happens to be a const expression example, but the same thing applies if it was runtime values. So I take a couple of things like this, add two distances together, do some comparisons with an operator greater than, even though I've done operator less than. And I then said, right, okay, that's distance and divided by time. That's going to give me a velocity. That's fine. And then converted it back out again. The interesting thing is in GCC gives you the answer saying it just compiles down to the answer is 5. So the generated code is basically just return the value 5. If you do this without constants, you will get an equivalent as the same that you would get if you just did it with doubles. So there is no runtime overhead to this one. It's all done at compile time. Okay, let's switch to a little bit of something else. There are other things that we may want to check. So here's a little fixed length string class. Fixed length string class, we're trying to avoid some of the problems that you get with C-style arrays with pointers to memory and you don't know how long it is. The classic buffer overflow problem. So this was something that you might use in embedded system, where you're going, well, actually, I want the kind of efficiency I get with const char star stuff, but I don't want to have the buffer overflow problems. So this string here, fixed string, notice in the middle n copy here, so we're copying into this into the buffer we've got. Notice it's not dynamically allocated, it's just inside the string. Use n copy, make sure it's null terminated. There's actually a policy decision based in there and embedded. This says I'm going to truncate my string. If you give me a string that's too big to put in there, you have a great long, you put war and peace into something and it's only 10 characters long, it's going to truncate it. Truncation may or may not be appropriate. It's a policy decision. But is that policy what you want? So, for instance, what might be some other valid policies? You might say, well, actually, look, I want to stick this in diagnostic log because something's not right there, but I'll just truncate it, but I'll note the fact that truncation occurred. And you may be displaying something on the screen, and it may just be a message where it's truncated, that's okay. If it's a message that's printing out a value and it truncates it, that might not be okay because it now gives you 3 digits of an integer or the 4 digits of an integer. Oops. So in a case like that, you might decide to throw an exception. You go, look, this is horribly wrong, and there's something bad here. We all need to recover from this somehow. If it's an embedded system, you may go, look, actually, I'm in a horrible place. I have no idea what's going on. I'm going to reboot. So there's something bad has happened here. You may be in a test environment and say, look, actually, I want to stop at this point, get in the debugger, give me a backtrace, go down here and go, where are we? Because I need to be able to do this one. These are all policy decisions that you want this string to be able to implement. So we can use a policy to this one here. So my fixed string here, instead of hardwiring in that n copy and truncate, I'm going to do all the copying, and if it's not 0 at the end, so I've got some form of truncation, I'm then going to call the overflow policy at that point to decide what to do. And this one here, by default, it's saying, okay, complain, just print something out to standard output. You can decide what you want to do. You can decide, you may create a one here, a noisy string that says it's resetting on that. It's going to make its presence felt very nastily when you do that. So these are policies that you can do. Let's just compare the policy in the CRTP approach. CRTP, essentially does a compiler downcast, and it's mixing in functionality. It allows you to say what you want with this one, and it's really a library injection technique, and it's a way of refactoring things out. Policies don't do downcast, they essentially do an upcast, or depending whether you inherit from that, or whether you call out to it. And this is useful for rules validation logic, such as constructors, because that was, if you notice, that one was a constructor. There's a validation policy inside a constructor. Just as we had validation for the limits of our types. So let's see how we can mix this all together here. So this unholy mess here of quantity that says, right, I have a public, I'm ordered of quantity, and I'm also inheriting from the constructor check. So I will do the initialization of that one, of the ordered one. That gives me all my relational operators. And then the constructor check will call the constructor of, in this case, it's non-negative checker. If it's less than 0, we're going to throw. So this is const_expr, which means that this can then be enforced at compile time. So if you try to create one of these things at compile time, it will do that check at compile time, and you won't even compile. So if you try to put a negative floating point, it won't compile. If you try to do this at runtime, it will obviously do the runtime check. So that constructor check there, you can initialize the string directly, but it's a little bit more entertaining to do. If the constructor check doesn't complete correctly, because that exception is thrown, that turns it into compiler error. If it doesn't throw, on the other hand, if that top part doesn't throw, essentially it gets removed. So you've done a compile check that then goes away at runtime. There's nothing left of it. So there are some useful things you can do with that. So let's see what that's done here when we put this extra check in here. const_expr negative number, compiler error. If we do it with a negative number here, you'll see it get a runtime throw. And if we do it without that, we get exactly the same as we had before. So there's a 0 overhead to that. Just to stand back from a little bit, what we've done actually is created this domain-specific embedded language, DSEL. So it's like a domain-specific language, but it's embedded in C++. We basically said, here's C++, we'll use these tools to produce our own language. If you use ints and floats, you're using an implicit interface. You're using what the language has given you. What we've done here is said, now we're going to go explicit. We're going to say, I'm going to take all control of these ones. Instead of saying, I get all the operations that I get on ints and floats, which causes me no work to create this, 0 work to create it. Easy to misuse, though. I can do ++ on something when I didn't mean to do that. What does that mean for your type? Little checking if you use the implicit interface. And it's wider than necessary. It doesn't allow you to constrain things. But on the other side, if you then go to the explicit interface, you say, I want only these things. You've got to do some work to do this one. Once you have those libraries, there are a number of those libraries around. Boost has something similar. But it means it's harder to misuse. And you get a lot more checking. And it's only as wide as you need. OK, so implicit versus explicit. There are some things, however, you want to happen implicitly. And typically, the destructors and the cleanup is something you want as an implicit interface. You don't want people having to do explicit cleanup. So I would say, from a safety point of view, you want explicit for all the operations, apart from the cleanup operations. So your resource management and destructors and cleanup and rollback, you want that to happen. You don't want to have to call cleanup things. In other languages, you have to go and call cleanup. In C++, destructors are huge part of good C++ code. In terms of resource management, there's that. So that means you want implicit safety operations, but for anything else, you want those to be visible and explicit. OK, so we have libraries. We've got let's compare the runtime and the compile time stuff. So on the top there, the OO view of the world is you say, well, I have a client and server class, and I have an interface in between, a Java-style interface or C# or whatever you want. And this has the advantage of allowing you independent compilation. If the client class here says, I'm going to call something that expects a string, and I try to pass on integers to it, it says, you can't do that. You get that independent checking. If the server says, I'm trying to call .length on an integer, it says no such method. So you can compile the client and the server independently. But you can only put those things together which you have thought about and said, this is a whitelist. This is pre-planned. You have to know that these things can be put together. With templates, on the other hand, and we'll come back to this concepts thing in a moment, you get a template of T and an X, and you go, oh, I'll just put them together. Do they have the right signatures? And it goes, yeah, I can do that. That's, if all the operations are correct, that's fine. If not, you get a horrible error long novel like this. It's like War and Peace. And this is one of the reasons you can't get separate compilation of templates, why you have header files, etc. And you need to see the inclusion model for templates. What happens if we try to get that kind of this similar separate compilation, or at least this checking of types with templates? And this is what concepts are about. So concepts are essentially trying to do kind of like that interface thing and applying some additional type information to template parameters. It's there. It's not in C++17, but you'll find GCC has concepts in it. So let's try them out. Let's see actually what we could do. How can we apply concepts to what we're doing? So here's my first attempt at this one. So you've got a concept, Boolean has operator less than. And it says, well, it's a Boolean, and it returns true if T1 less than T2 is a valid expression, if you can do that. Okay, so I can now take my ordered and say, has operator less than. So instead of template type name, it's template has operator less than. And that then should allow you only to put in to this one things that have an operator less than. So let's actually try it. Class year, public ordered year. Damn, this doesn't compile. And the reason it doesn't compile is because ordered is looking for something that says, well, I don't know what's in year, so I don't know whether it can satisfy this. So I've got, although I can use CRTP with inheritance and other things, I can't use it with concepts, which is annoying. And I had a scratch on my head and said, well, how else could we do this one? So this does actually work. So I've tried this on GCC. Same concept, but notice instead of having a constrained template argument like that, I've had before type name, I've now put a requires clause afterwards. If you've seen C#, C# has a requires clause similarly to that. So my operator greater than, you can only pass in something that says has operator less than derived. Now that works. So one of the reasons for doing this is we think, actually, yes, we can have some fun with this. Let's try it. Let's see what the error messages might look like. So here are the error messages without concepts. So I have my struct x ordered like that, and then I try to call operator greater than when x obviously clearly does not have an operator less than. So this particular thing says, blah, 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 required from here, no match for operator less than in this. And it's one of those confusing messages. You look and said, I was calling operator greater than. Why is it saying operator less than? So that's one of the problems you get if you try to do this. With concept, on the other hand, it says, look, operator greater than can't do that one because does not have operator less than, blah, blah, blah here, and this expression at the bottom, T1 less than T2, would be ill-formed. It's a longer message, but it's at least pointing in the direction that says where those things are. I'm expecting that the compilers will get better at these messages. I'm hoping, because that's not particularly nice. Let's see what the fixed string thing might look like if I try to call out to something that doesn't have overflow on it. So the top one there is without the concepts. And I try to call this one fixed string for x, and it says no overflow like this. With the concept, it says, oh, that x can't do that one because it hasn't got overflow, because overflow, blah, 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 would be ill-formed. So at least it points you in the right direction. So, a summary of this one. Essentially, we're providing lightweight abstractions that allow us to control what we do, that allow us to write safer code, that allow us to have the compiler do more checking for us, and allow us to put more domain knowledge into our code and have it checked. And if you're doing anything that requires safety, anything that requires correct answers, this has advantages. It has 0 or small runtime overhead, usually 0 in terms of CPU or memory. The use of these ones, so there's 0 or little overhead to the developer for this, once you have those libraries in place. And allows you to create those ones. And I don't promise that everything will turn into just a single instruction. Okay, any questions about that?